thank you for standing by. Today's call will begin momentarily. Again, please continue to hold. Welcome and thank you for standing by. I'd like to inform all parties that today's call is now being recorded. If you have any objections, you may disconnect at this time.
Over 200 million miles away from Earth, OSIRIS-REx is preparing for NASA's most ambitious sample return since the Apollo program. After months of detailed analysis of Bennu's terrain, the team selected the Nightingale crater as the sample site for the mission. OSIRIS-REx will need to carefully dodge rocky hazards as it descends to a space no larger than a few parking spots. The spacecraft has mapped the terrain in high resolution, capturing a stunning catalog of images across Bennu's rough surface. And now, we are ready to target Site Nightingale for the touch-and-go sampling event. OSIRIS-REx is prepared to begin its descent down to Bennu's surface and finally collect a sample. Using its database of images from Nightingale as a guide for its onboard navigation system, Natural Feature Tracking, OSIRIS-REx will steer itself to the tag location, dodging Bennu's rocky hazards along the way. After years of preparation, analysis, and rehearsals, our target is in sight. OSIRIS-REx is ready to tag. Over 200 million miles away from Earth, OSIRIS-REx is preparing for NASA's most ambitious sample return since the Apollo program. After months of detailed analysis of Bennu's terrain, the team selected the Nightingale crater as the sample site for the mission. OSIRIS-REx will need to carefully dodge rocky hazards as it descends to a space no larger than a few parking spots. The spacecraft has mapped the terrain in high resolution, capturing a stunning catalog of images across Bennu's rough surface.
Okay, well, thank you everybody for looking at our video. I'm Greenhouse Loma with NASA's Office of Communications.
And now,
welcome to our countdown to tag
target Site Nightingale for the touch-and-go sampling event.
Team, which next month is going to be
OSIRIS-REx
something
is
incredible,
prepared to begin its
become the
descent
first NASA
down to
mission to
Bennu's
sample an
surface
asteroid.
and finally
What you
collect
just
a
saw is
sample.
the premiere of our new mission trailer tells
Using
the
its
story
database of
exciting
images
mission.
from Nightingale,
If you're at nasa.gov/live, the charts and videos our speakers will refer to will show up in the viewing box there, and a web feature describing tag in detail is posting to nasa.gov and the OSIRIS-REx page with the links as well. OSIRIS-REx is part of NASA's New Frontiers program, which tackles specific solar system exploration priorities of the science community. Its siblings in the program include New Horizons, the visitor to Pluto that is still studying our solar system, the outer solar system, Juno, which is making amazing studies about our turbulent neighbor Jupiter, and Dragonfly, which is slated to fly a rotorcraft to Saturn's moon Titan in the 2030s. OSIRIS-REx will take a sample of ancient solar system gravel that has been lying on the surface of asteroid Bennu for thousands of millennia to unlock a record older than our planet. The mission team persevered through their surprise upon arriving at Bennu, and they found that the asteroid's surface was much rockier than they'd expected, but the team adapted instruments, studied, learned, and stayed on the mission's course. And later they persevered through the challenges of operating this complex mission during a pandemic. 9 months ago, we announced Nightingale as our primary sample collection site, and now we're on the cusp of the amazing maneuver to do that sample collection. Here to share the inside story of this incredible mission, we have with us a panel that includes Thomas Zurbuchen, NASA's Associate Administrator for Science, Lori Glaze, Director of NASA's Planetary Science Division, Principal Investigator Dante Loretta, who leads the mission from the University of Arizona Tucson, Mike Moreau, who is OSIRIS-REx Deputy Project Manager at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and Sandy Friend, who is OSIRIS-REx Mission Operations Manager at Lockheed Martin Space in Denver, which built the spacecraft. So now, as we count down to tag, let's hear from our panel. Thomas?
Well, I'm so excited to be part of this today, and of course, it is NASA's first mission to return an asteroid sample, and this space story started on September 8th, 2016. Yes, it's almost 4 years ago. Of course, it launched. You see that picture there on the United Launch Alliance Atlas V rocket. And returning a sample is hard, and it's hard because of the many phases of the missions and the accuracy and all of this, but COVID made it even harder. And I really want to start my comments by thanking the entire team from the University of Arizona, from Goddard, Lockheed Martin, and everybody else who's active part of that. And down here at the lower right, you see Sierra Gonzalez, Lockheed Martin systems engineer, and it was taken April 14 during one of those rehearsals, a checkpoint maneuver. You know, the one in August 11, of course, got OSIRIS to within 40 meters of Bennu surface, and you see the picture there just next to my portrait at the bottom of that. But I just looking at Sierra, I just want to recognize that she's one of many who are working to make this happen with all the challenges that are around them, many more than we thought we would have to deal with there. So I'm just so grateful. OSIRIS-REx is a mission of international partnerships, and I want to thank at this moment in time the international partners, especially the Canadian OSIRIS-REx laser altimeter team. That is critically important. We'll share some of the collected sample with Canada on the return. We also have an agreement with Japan to share our respective asteroid samples. Of course, Hayabusa 2 and OSIRIS-REx are both sample return missions, and we're just so excited to be partnering to benefit both science teams through that partnership. Of course, the scope of sample returns is all about time capsules. Bennu is a time capsule. It has been out there since the Earth's beginning for 4.5 billion years and carries the history of that environment with it. We didn't even know Bennu existed until it was discovered in 1999 via a telescope by NASA's Near-Earth Object Observation Program, a program that, of course, is very important for us and helps us find near-Earth objects of potential danger to the Earth. The OSIRIS-REx spacecraft, I'm going to talk about the middle there, is about the size of a 15-passenger van. You've seen those, you've sat in them, and the sampling site is just about the size of, 8 meters or so, 26 feet in diameter, a few spaces of parking lot. So you say, how big is the crater that this has to be hit? Well, it's about the size of a tennis court. So think about those movies you've seen, some of these sci-fi movies, some vehicle coming in on a kind of tennis court size thing, and, a kind of size of a vehicle and hitting it right there in the middle where it's marked, and taking these samples and flying back out. So it's making that impossible possible. That's what this team is doing, and we're so excited for that. And you see it on the graphic there. More will be said about this. And of course, I just want to remind you that, and I think you said it, Gray, earlier, that Bennu presented tremendous challenges. As first of all, it's not nearly the sandy beach we hoped it would be, or we expected. Well, exploring nature is about surprise, and certainly this team had a lot of it. There's also, Bennu is an active body, we've learned, and there's amazing publications that already come out about these baseball-sized objects that are flying off it, obstacles that are there, kind of over and above all difficulty we already knew would be there. So it really requires incredible system engineering and an autonomous navigation system and mapping capability that rivals the kind of things that we do on Earth, perhaps autonomous driving are kind of the things that we're doing here on Earth, and it's just the technology is super exciting. We're going to hear some about it, and so I just really look forward personally about this TAC event. I can't wait to meet many more of the team members, and again, I want to thank them for all the incredible work that they're doing under difficult circumstances, but the success they're creating. We're ready for it. I want to just turn it over to you, Lori Glaze, as Grace said, the Mission Director of Planetary Sciences. Lori, please take it away.
You bet. Thank you, Thomas. If I could have my first graphic, please. I'm Lori Glaze, as Thomas said, and Gray introduced. I'm the Director of Planetary Science at NASA headquarters. And I want to begin just by echoing Thomas's sentiments about thanking the team. This is an incredible mission, and I couldn't be any more proud of the work that has been done to keep everything moving forward in these truly unprecedented times. But now we're at Bennu, and Bennu is one of close to 1 million known asteroids in our solar system. Asteroids are, as Thomas just said, relics of the earliest material that formed the planets in our solar system, and they hold key information to unlocking our understanding of how the solar system formed and how it evolved. Missions like OSIRIS-REx, which is shown in the middle of my graphic there, as well as other missions like Psyche, which is shown in the middle on the bottom, visiting 7 Trojan asteroids around Jupiter's orbit, or DART, the mission, the Planetary Defense Mission, to demonstrate asteroid redirection in the left there on the bottom, or even Psyche, which is another NASA mission to go to a potentially metal asteroid, as well as another mission not even shown here, New Horizons, which is exploring the Kuiper Belt. All of these missions are addressing major components of asteroid science, as well as advancing NASA's planetary defense efforts to help us better prepare for how to respond to asteroids that may threaten Earth in the future. The returned samples from OSIRIS-REx are going to be able to help us answer key astrobiology questions, such as how water and organic material were delivered to Earth and the role that those key ingredients have played in the early initiation of life on Earth. Sample return is an important strategy for NASA and for planetary science. From the Apollo lunar samples that are shown on the top left there, where we're opening up one of the samples that's been preserved since Apollo 17, and was just opened recently over the last year. So from Apollo lunar samples to OSIRIS-REx, and then in the future, our eventual return of samples from Mars, which we're now in the process of planning for in the coming decade. And the reason why these returned samples are so important is because on Earth, we can apply the full breadth of our terrestrial science laboratory capabilities to study the physical and the chemical characteristics of these pristine, unaltered materials in our state-of-the-art laboratories. And with Bennu specifically, we'll be able to do so within the context of the remotely sensed data that's been obtained while the OSIRIS-REx spacecraft has been orbiting Bennu. And these samples returned from Bennu will also allow future planetary scientists to ask questions we can't even think of today, and to be able to use analysis techniques that aren't even invented yet. And all of this, of course, will continue to help inspire the next generation of explorers. So with that, I'd like to toss it over to Dante Lauretta, the PI for OSIRIS-REx, and he can tell us a lot more about the mission and what's ahead.
Thank you, Lori, and thank you, Thomas. If you could bring up my first graphic, please. So I've been involved in this program for over 16 years now. When I first was invited in 2004 to work with the original principal investigator, Dr. Michael Drake, who was the director of the Lunar and Planetary Laboratory at my home institution of the University of Arizona, and my boss at the time. And I was a young assistant professor, and it was a great honor for Mike to ask me to support him in the development of this mission concept. And my job was to come up with the science investigation, and through that thought process, I developed the name of the mission. As Lori mentioned, this is all about understanding our origins, addressing some of the most fundamental questions that we ask ourselves as human beings. Where did we come from? And are we alone in the universe? And we chose Bennu very early on in our mission design because we felt it had a good chance to be full of organic material and hydrated minerals, so that we could understand if objects like Bennu led to Earth being a habitable planet, to being a water world, and to sparking the origin of life. That information was based on a technique we call spectroscopy. And these are, because they're carbon-rich asteroids, they're generally very dark. They reflect very little sunlight. So understanding or interpreting their spectra is a challenge. And one of the aspects of the OSIRIS-REx science program is to understand these dark, low reflectance asteroids and try to infer their composition from that information. Lori mentioned over 1 million known asteroids in the solar system. We're not going to send spacecraft to every one of those, although NASA's making a pretty good run at it with this amazing fleet of asteroid exploration missions that are on deck following OSIRIS-REx. We're going to use spectroscopy, and we're going to use the OSIRIS-REx samples to better understand the spectra of these objects. Back in 2004, when I was coming up with the mission name, I thought I was thinking very futuristically about asteroids as resources. And in fact, we are now looking at that as a species, as opportunities for development of in situ resources to further exploration of space, with water being a key target because you can produce liquid hydrogen, liquid oxygen, and make rocket fuel. And most importantly is we are worried about near-Earth asteroids as potential hazards, so there's a security aspect to our investigation. Bennu is one of the most potentially hazardous asteroids, with a non-negligible chance of impacting the Earth at some point in the 22nd century. And part of our science investigation is about understanding its orbital trajectory, refining the impact probability, and documenting its physical and chemical properties so that future generations can develop an impact mitigation mission if that's necessary. And then finally, we're all about bringing back the regolith. Regolith is the loose blanket of rock and dust that covers these airless bodies like asteroids and the moon. And we're exploring the asteroid in great detail to identify locations of regolith that we can collect to bring back to our laboratories for further investigation. If I could have the next graphic, please, and start the rotation movie. So we did a lot of work characterizing Bennu telescopically prior to launch. Unfortunately, Mike Drake passed away in 2011. We were selected as a NASA mission in May of that year after spending 7 years in proposal and concept of refinement. And so I became the principal investigator, and he passed that mantle on to me, and it's something that we carry forward in his memory. Throughout that time, we were looking to understand the nature of the asteroid surface, and we had some really compelling information to suggest, as Thomas said, that the surface was beach-like. Sand-sized particles were dominating its surface. That was based on information from the Spitzer Space Telescope, which is an infrared telescope that NASA operated that tells you about how asteroid surfaces heat up and cool off, and it looked like a beach in terms of how fast it heated up and cooled off. We had fantastic radar data from the Arecibo and Goldstone radio telescope, and it looked very smooth at radar wavelengths of a few to 12 centimeters. And we knew it had this amazing spinning top shape with the bulge at the equator, which we thought was due to the movement of fine-grained material to that equatorial region and piling up of a gravel ridge. And then we got these images that you see spinning here before you. These are still some of my favorite images of Bennu. These were the first full disk shots that we got as we approached the asteroid in December of 2018. And I knew right away we were in for a challenge. First of all, there is nothing that looks like a beach anywhere on this asteroid. Instead, it is covered by boulders. This is a rough, rugged, rocky surface. We had designed the spacecraft to target areas 25 meters in radius. There is nothing that big on the surface of the asteroid that looks like it's sampleable with our TAGSAM device. So we had a challenge in front of us, and the team rose to that challenge, spending all of 2019 mapping this asteroid in exquisite detail with cameras, with our laser altimeters, and with our amazing spectrometers. So if I could have my next graphic, please. This just shows a couple of the key science highlights, some of the most memorable results so far from our mission. First off, in the upper left there is a section of the spectra from one of our instruments, the visible and infrared spectrometer that we call OVIRS. And I know these spectra are difficult to understand if you're not an expert, but you're looking at how the asteroid surface, in this case, is reflecting sunlight. and they should be smooth. We've subtracted out the solar spectrum, and so if it was reflecting all the light equally, this would be a flat line. But instead that we see the signal drop substantially at a wavelength of about 2.7 microns, which is in the infrared and beyond what human eyes can see, but still indicating that there is something on the surface that is absorbing that light, that's taking that energy out of the solar spectrum. And that's due to a chemical. And in fact, we know this area very well, and that is due to the presence of water. So this was an incredibly exciting result for us. Basically, we got this part right with our telescopic observation. We selected Bennu because we were hoping it was hydrated. Hydrated materials are often associated with organic rich material, exactly the kind of sample that we wanted to bring back to our laboratories for our investigation. So Bennu really delivered for us here. And I can't tell you how excited I am to get those samples back into our laboratories and begin that sample analysis phase of the mission. And then Thomas mentioned probably one of the biggest surprises after the rough and rocky surface was these particle ejection events. This turned out to be actually pretty good news. It was a little scary at first. We saw these eruptions of particles from centimeters down to sub-centimeter sizes blasting off the surface of the asteroid regularly. We've seen hundreds of these events over the course of our operations around the asteroid. The best news right away was, since these particles, some of them were less than a centimeter across, that's the kind of stuff that we can pick up with TAGSAM. So we had our first direct visual confirmation of sampleable material existing in the vicinity of the asteroid. Most of the particles that launch off the surface actually impact back onto the asteroid. So I knew somewhere there was going to be fine-grained material that we could collect. And then the other real bonanza that came out of these ejection events was some of the particles, when they launch off the surface, they get accelerated by solar radiation pressure, kind of like a light sail, and they launch into orbit. And they go around the asteroid for multiple revolutions before re-impacting back on the surface. And because we have hundreds of them, this allowed us to probe the gravity field of Bennu at a scale we never thought possible when we were designing the mission. So we have a really great understanding of the distribution of the gravity field around the asteroid as a result of tracking these particles. If we could go to the next slide, please. And this is an animation, so please start the movie. So one of the great things that we did was we used that Canadian Space Agency provided laser altimeter to map the topography of the asteroid surface at scales down to about 5 centimeters. Unprecedented in our ability to understand the topography of a planetary body at this scale. And then we were able to overlay on top of that high-resolution images from our Polycam instrument built here at the University of Arizona. And with those data sets in front of us, we were able to identify regions of interest for possible sample collection. And we ended up with the final 4 sites that were driven largely by the fact that they appeared to have fine-grained material at the surface that was very distinct from the average rough, rocky, boulder-strewn areas that we saw over most of the asteroid. And we ended up selecting this site here that the movie focuses on, which we call the Nightingale Crater. By far, Nightingale has the most abundant fine-grained material. We made this selection announcement in December of 2019, and then we spent early 2020 doing low-altitude reconnaissance passes over this site, ultimately imaging at 3.5 millimeters per pixel, basically microscopic images of the surface covering the entire crater, and we counted all of those rocks. We have a team of students here at the University of Arizona that are expert asteroid rock counters, and they counted hundreds and thousands of rocks at the scale of 2 centimeters and smaller. So we knew Nightingale was the place to go to collect our sample site. It also has a great signal for hydrated minerals. It looks like a relatively fresh crater, so the material hasn't been exposed to the space environment for very long. So once we made the decision that this is where we were going to go to get the sample, the science team's job was largely done, although they did provide a lot of support for the spacecraft systems that you'll hear more about. So I turned to my deputy project manager, Mike Moreau. I said, Nightingale's the target, make it so. And I'm going to turn the presentation over to Mike to tell you how the team has risen to that challenge.
Thank you, Dante.
This is Mike Moreau, and I'm the Deputy Project Manager for OSIRIS-REx at Goddard Space Flight Center. And I'm going to tell you a little bit about what's going to happen during the TAG event and also the preparation that our team has been doing this year to get ready. If you could please advance to my first graphic. Since the primary and backup sample collection sites were announced last fall, our team has been busy preparing to tag either at the Nightingale site or our backup site, Osprey. Beginning in January, as Dante alluded to, we conducted 2 low reconnaissance passes over each of the sites. These low flybys, first at an altitude of 500 meters, then 250 meters, collected high-resolution imagery that was used to build the final 3D maps used by the spacecraft's onboard navigation system, or NFT. As Dante mentioned, this data was also used by the team to map out regions where fine-grained material is present in each site, and calculate the likelihood of collecting a sample at different points where the spacecraft might contact. The team conducted 2 TAG rehearsals, first in April and then in August, which took the spacecraft progressively closer to the surface each time. The rehearsals allowed us to check out the systems and software necessary for a successful TAG attempt. Basically everything except for the final few minutes before we touch the surface of Bennu. The animation that you're seeing right now is a series of images that were recorded by the SAMCAM during the final rehearsal in August, as the spacecraft descended from approximately 128 meters to about 44 meters, just before the rehearsal was terminated. In these dramatic images, you can see the sample collection arm and the TAG SAM extended into the field of view of the camera. Towards the end of the sequence, you can see the Nightingale site just coming into view at the top of the frame, and the spacecraft is seen passing over a very large boulder. That rock, which is the size of a 2-story building, looming over the eastern edge of the Nightingale crater, is reverently referred to as Mount Doom by members of our team. If you could advance to my next graphic and start the animation. This animation is showing a trajectory. The trajectory that the OSIRIS-REx spacecraft will follow during TAG, and some of the perspective of the spacecraft will have during this event. Starting from a 1-kilometer orbit about Bennu, TAG begins with a propulsive maneuver causing the spacecraft to depart orbit and transit across the sunlit side of Bennu towards the vicinity of the Nightingale site. Shortly after leaving orbit, the spacecraft will deploy its sample collection arm and slew to point the navigation camera towards Bennu. When reaching an altitude of about 125 meters above Nightingale, the spacecraft fires its thrusters to perform the checkpoint burn, which puts it on an intercept trajectory with the surface. About 10 minutes later, or about 45 meters above the Nightingale site, thrusters fire to perform the match point burn, which sets up the precise contact time and velocity for TAG. Then about 10 minutes after match point, or about 4 hours after leaving orbit, the TAG SAM mechanism will briefly make contact with the surface. A nitrogen gas bottle will fire, material will get stirred up and captured in the TAG SAM, and the spacecraft will fire thrusters to back away. So years of planning and hard work by this team are essentially coming down to putting the TAG SAM into contact with the surface for just 5 to 10 seconds. This basic concept and timeline for TAG that you're seeing in this animation has not changed since very early in the development of the mission. But as Dante alluded to earlier, Bennu has not made things easy for us. When we first saw the rugged boulder-strewn surface, our team knew immediately that we would need to adapt our methods and come up with some new capabilities in order to safely collect a sample. There were just no places on Bennu that even came close to what we had designed the system for. So our awesome team got to work. If you could bring up my third graphic. This graphic illustrates 2 new capabilities that our team implemented on the spacecraft, without which it would be impossible to tag at Nightingale. The left area of the graphic illustrates the concept of natural feature tracking. The onboard navigation capability implemented by our Lockheed Martin partners. Throughout the entire 4-hour tag trajectory, images recorded by the navigation camera are processed by the NFT system onboard the spacecraft and used to update our estimate of the spacecraft's trajectory on board. Shortly before the checkpoint and match point maneuvers, the position and velocity estimates from NFT are used to autonomously retarget checkpoint and match point burns to account for trajectory errors and correct to the targeted tag coordinates. The right side of the figure illustrates the concept behind a hazard map that we're using on the program. There are many spots around the vicinity of Nightingale and some within the crater itself that could be hazardous to the spacecraft if it were to touch down and tip over slightly during the sample collection. The hazard map identifies all of these potentially hazardous areas around the site, and those are shaded red on the graphic. When the spacecraft reaches an altitude of 5 meters, the NFT system will predict the contact point with the surface, compare it against the pre-calculated hazard map, and if we're coming down on an unsafe area, the system will execute a backaway burn and wave off the tag attempt. These two innovations are critical to tagging at Nightingale. But the other major adaptation our team made was to dramatically improve the performance of the OSIRIS-REx system. Our team refined models of the small forces acting on the spacecraft, carefully calibrated the performance of the thrusters to execute velocity changes with a precision below 1 millimeter per second, and extracted every last ounce of performance out of the NFT system. As a result, we can reliably deliver the spacecraft to an area on Bennu that is more than 10 times smaller than what was originally designed to. And this accomplishment is due to the incredible hard work and innovation of our navigation team members at Kinetics and Goddard, working together with members of the Lockheed Martin Flight Operations team. If you could advance to my next graphic and press play. This visualization attempts to convey the size and scale of Nightingale and the challenge of navigating OSIRIS-REx to tag in this location. The orange circle that you can see shows the original size of the tag region that OREX was designed for, an area of 50 meters diameter projected around the Nightingale crater. The blue circle is about 8 meters in diameter, and this shows the primary safe area within the Nightingale crater that we're targeting and where we expect to actually contact the surface. This spot is just the width of a few parking places and is surrounded by large boulder-like structures the size of small buildings. So for some perspective, the next time you park your car in front of your house or in front of a coffee shop and walk inside, think about the challenge of navigating OSIRIS-REx into one of these spots from 200 million miles away. So I'm going to end my remarks by talking about some of the things that could go wrong when we finally touch Bennu. In spite of the incredible perseverance this team has shown in responding to Bennu's challenges and their dedication in keeping this mission and these milestones on track in these unprecedented times that we're living in, we may not be successful on our first tag attempt. And for that reason, our team is fully prepared to make a second attempt at our backup site Osprey in January if it's necessary. If you could pull up my fifth graphic, this shows two of our primary measures for our chances of success at Nightingale. On the left is a map that represents our assessment of the best places in Nightingale for gathering the fine-grained materials that the TAGSAM was designed to collect. On the right is a visualization of the hazard map, with the safe areas designated green and the regions that could result in abort in yellow and red. I've already spoken about how the hazard map will keep the spacecraft safe by triggering a wave off if we're coming down in an unsafe location. We've calculated an approximately 6% chance that we could find ourselves on a trajectory that would result in a hazard map wave off. A more likely scenario is we touch down nicely in a safe location, but we fail to come up with a good sample. Our measure of success for sample collection is that we bring home a minimum of 60 grams. But the TAGSAM is designed to ingest only small particles that are roughly 2 centimeters in diameter, or roughly the size of a U.S. nickel. If the TAGSAM contacts any of the blue areas shown in the sampleability map on the left, we believe we have a great chance of collecting well in excess of our 60-gram minimum requirement. However, there is up to a 30% chance we will contact in one of the pink areas, in which case we are likely to come up with an insufficient sample. So one final note about this figure, you can see that there's a small cross in the center that designates our targeted landing location. That's where we're trying to touch down. and the small circular area just to the left of that shows the actual contact point that we would have had if we had continued to the surface during our match point rehearsal in August. If you could bring up my final graphic, please, and push play. This is a series of animations that helps illustrate a few of these what-if scenarios of some of the things that could go wrong. The first clip illustrates a wave-off triggered by the hazard map. After the match point burn, the NFT system is predicting the point of contact with the surface and compares this against the hazard map on board the spacecraft. In this particular scenario, the spacecraft is descending onto some large rocks that were flagged as hazards, so the spacecraft will, when it reaches 5 meters, performs a back-away burn. We stop this tag attempt before we ever reach the surface in this case. The second clip illustrates one of the scenarios in which we don't collect a sufficient sample. In this case, the spacecraft's on target, the TAGSAM touches the surface and the gas bottle fires, but unfortunately the TAGSAM head is tipped up on a rock, and much of the nitrogen gas escapes out the side without allowing us to capture much material in the TAGSAM. The third clip illustrates a similar scenario, this time in which the TAGSAM touches down on a pile of rocks. In this case, there's just very little material that's present to be collected in the TAGSAM. So Nightingale is literally the best place that we found to collect a sample on all of Bennu, but as you can see, it still presents a lot of potential challenges. All of this said, by far the most likely outcome that we will have on October 20th is we will contact the surface and come away with a large sample that exceeds our minimum requirements. But Bennu has thrown us a number of curveballs already, which is why we are fully prepared to tag at the Osprey site if that becomes necessary. So now I'd like to turn it over to Sandy Friend, who is the OSIRIS-REx Program Manager at Lockheed Martin, and she'll talk a little bit more about the sample collection process and the sample return capsule. Take it away, Sandy.
All right, thank you, Mike. As Mike mentioned, I'm going to talk a little bit more about how we collect the sample from the surface of Bennu and bring it back to Earth. We do that with our TAGSAM, which stands for Touch and Go Sample Acquisition Mechanism, which was developed here at Lockheed Martin. The TAGSAM sampler head sits at the end of our TAGSAM arm, which is approximately 11 feet long. It looks a lot like an air filter that you might find in an older vehicle. It is designed to collect that smaller fine-grained material, as Mike mentioned. It's capable of ingesting material of 2 centimeters or less. So it's very important that we have the precise navigation to get us to the areas on Bennu that are considered sampleable. So if you start the first animation, you'll see the spacecraft slowly descending to the surface of Bennu. When it declares contact by our onboard microswitches or our accelerometer, we'll fire one of our 3 nitrogen gas bottles. This will cause the surface material to mobilize and become entrained inside the sampler head. This is much like a reverse vacuum cleaner, in which we will then have our surface material or regolith secure inside the sampler head. We estimate that our time on the surface will be between 5 and 10 seconds before the spacecraft backs away with the sample safely inside of the sampler head. In the days after tag, we'll perform a couple of activities on board the spacecraft to determine how much sample we've collected. Dante is going to talk a little bit more about that in just a couple of minutes. When we make the decision to stow the sample, it is a multi-day activity. It's very important that we get the arm manipulated just right, take images, verify things on the ground before we're ready to put it inside of our sample return capsule. If you start the next animation, this will show the final steps of our stow sequencing. You'll see the onboard sample return capsule open. The arm will be manipulated near the science deck, and the sampler head will be moved to just the exact angle that is required to place it inside of the SRC. The sampler head will latch into our onboard capture ring. We'll do a small tug test just to make sure that it is secure before we go ahead and detach the sampler head from the arm. The arm will then move back into its parked position for the final time alongside the spacecraft, and we will close the sample return capsule, keeping our Bennu samples nice and safe for the return journey home. We'll depart Bennu in March of 2021 and embark on a 2.5-year cruise back to Earth. Our Earth return date is actually 3 years from today, September 24th of 2023. My final animation, you can see the spacecraft flying near Earth and releasing just the sample return capsule. It will re-enter and parachute safely to the ground at the Utah Test and Training Range, delivering our Bennu samples to the eager scientists to begin their analysis. I'm going to hand back over to Dante now to talk a little bit more about how we determine how much sample has been collected and how we make the decision to stow the sample or return for a second tag attempt.
Thank you, Sandy. So on the day of tag, October 20th, we will have a slow data rate coming in. We're talking to the spacecraft. Actually, the spacecraft is talking to us at 40 bits per second. So we're not getting a lot of information about how much sample we collected. We will know that the sequence executed on the spacecraft appropriately, if we made contact, and that we backed away. So over the next week or so, we'll be doing a series of activities to understand how the tag event worked and do as much as we can to verify that we collected our minimum of 60 grams of sample or more. We'll start out by looking at those images like Mike showed at the beginning of his presentation, where our SAMCAM instrument is watching the tag SAM head, documenting this contact with the asteroid surface. So we'll be able to tell if we were tilted, if the gas flew out to the side, if material was significantly mobilized. We'll also have a very good indication of the exact location in Nightingale where we made contact, and we can compare that to our sampleability map, which Mike also showed, to indicate, do we think we landed in an area there was abundant sampleable material, or were we in one of the more rocky locations with larger fragments? That sampleability map assumes that the rocks are solid and immovable, and there's a good chance that there's going to be some compliance of the surface, and maybe we'll push them away. We also think that the rocks may be crushable, and that maybe we can still collect material even if we go into a sampleable region, or a region of the sampleability map that's indicated red. But we'll also have some direct confirmation. If you could start my next graphic and play the animation, we're going to be able to look at the tag SAM head with the SAMCAM in a variety of different orientations relative to the sun and relative to the camera. The tag SAM head is on a wrist joint that allows us to move it over a range of angles, so we'll be able to see the bottom of the tag SAM. And in addition to the gas stimulation technique that Sandy mentioned, you can see on the base plate of tag SAM, there's a series of what appear to be discs. Those are actually contact pad samplers. So simply by making contact with the asteroid surface, this is like our backup technique. We can pick up grains as large as 1 millimeter in diameter. A valuable sample because it'll represent the material right at the surface of the asteroid in its own right, and also a contingency in the event that something didn't work well with the tag SAM gas injection to push material into the larger filter container. We'll also be able to see any dust or other material that's on other areas of the tag SAM, like on the arm, on the blanketing that's covering the gas bottles, to get an indication, did we move a lot of material around when we made contact? And maybe, just maybe, we'll be able to see some of the particles in the interior of tag SAM. We're not guaranteed to get those shots, but we might be able to do it if the particles are in the right location and we get the right illumination conditions. So we'll have the SAMCAM imaging from the contact with the asteroid surface, and then we'll have the follow-on imaging of the tag SAM head itself to see if we can get visible confirmation of sample collected. Then we institute a really clever technique, which is demonstrated in my next video. So if you could start that, please. The spacecraft guidance, navigation, and control team has come up with this amazing way of measuring the mass of the sample inside the tag SAM head. Now, normally on Earth, when you want to measure the mass of something, you put it on a balance. Well, the balance requires that you have a gravity field. We know Bennu has a gravity field, but it's incredibly tiny, 10 micro Gs, or millionths of a G, compared to what we have here on the surface of the Earth. So a balance was right out. What we needed to do is try to understand some property of the spacecraft that would change with mass in the tag SAM head. And we settled on what we call the moment of inertia. The moment of inertia is a physics term that describes how mass is distributed and how it affects the rotation of the body around a central axis. So you can see what we're going to do is we're going to put the TAG-SAM out in what we call the plus X direction of the spacecraft, so different orientation than it is in the sampling configuration, and we're going to slowly spin the spacecraft around using the reaction wheels. We will do this before we tag, so we'll know what the moment of inertia of the spacecraft is when the TAG-SAM is empty, and then we'll do it again after we tag, and we'll see if the moment of inertia changed, and if that change is attributable to mass collected in the TAG-SAM head. And this has several tens of grams precision, so we should have confidence that we have 60 grams of material if we get a sample mass measurement value of about 79 grams or larger. We estimate that's a 90% confidence of 60 grams or more in the TAG-SAM head. So that's kind of the magic number that we're looking for. Anything below that, then we're having a conversation with Thomas and Lori, assessing the state of the spacecraft and its ability to go in for a second tag, and making a decision. Do we want to keep what we have, or do we want to continue to go on for a second tag attempt to meet the baseline requirement? However, I'm confident that we're going to have abundant material based on the nature of the Nightingale site and the extensive testing that we did with our TAG-SAM. If you go to my final graphic and start that animation, when we first started designing this mission and the Lockheed Martin engineers were asking me what are some of the most important aspects of the sample to bring back, the first thing I said was bring back a lot of material. I had worked on the Stardust samples that NASA had returned from Comet Build 2, and those provided some amazing insights into the nature of cometary dust. But we were also really challenged by the small size of the particles that were returned. I said, bring back big samples. 2 centimeters or so is plenty of material for us to understand the nature of the rocks on the surface, and try to bring back a lot of them. The requirement is 60 grams. That's based on the science team, where we've looked at all the laboratories across the world that we want to send material to, and how much material do we need to get the information about the organic chemistry, the hydrated minerals, the ages, exposures, all kinds of information about the sample. So the science needs the 60 grams, but TAG-SAM actually was tested to pick up at least 150 grams. And in the best case scenario, where the TAG-SAM filter is filled up, and you can see at the end of this animation where the TAG-SAM becomes transparent, the large amount of material that's possible to collect with TAG-SAM, we might have a kilogram of sample or more. So I can't tell you how excited I am. We're spending a lot of time on the science team now thinking forward to the sample analysis phase, lining up laboratories all around the world, and getting ready for the exciting announcements in late October about how much mass do we think we have and how much is coming home, which will really help refine our sample analysis activities. So with that, I'm going to turn it back over to Gray. And thank everybody for the presentations today. I'm really proud of this team, how far we've come, and I'm confident that we're up to the challenge that's ahead of us.
Okay, thanks, Dante, and thanks everybody for that incredible detail about the amazing challenges this mission has to go through to get this sample. As Dante said, we're going to take questions now, and you need to press *1 to get in that queue. We have a lot of people online, and we're going to ask that you limit yourself to one question. Please say your name and what outlet you're with, please. And while we're waiting for people to get in line, just wanted to remind everybody that a feature explaining TAG in detail, along with links to all the graphics and videos that you just saw, is posted right now at nasa.gov. And we are ready for our first question, operator.
The first question comes from Mike Wall. Your line is open.
Thank you all. Mike Wall, space.com. This is probably for Dante. So what will the next, like say 3 weeks and a bit be like for you guys and for the whole spacecraft team? What sorts of rehearsals are going to be coming up in this home stretch to the operation? Can you just lay that out for us about what you're going to be doing over the next 3 weeks to prepare for this?
I can tell you what I'm going to be doing, but I actually think Sandy's probably better to answer the questions about what the spacecraft team is doing to get ready for TAG. I'm focused on helping communicate the importance of OSIRIS-REx and the exciting science that we're preparing for, recognizing the team and all the hard work that they've put into this as much as possible, and really planning on ways that we're going to be able to celebrate in the amazing, challenging pandemic conditions that we're in. I'll be traveling up to Denver from Tucson on October 15th and joining the team live there for the actual sample event. But I think Sandy's better positioned to talk about spacecraft activities over the next few weeks getting ready for TAG.
Yeah, I can certainly talk more about that. We are finishing our test program here, a lot of the what-if scenarios. There are some onboard activities that need to take place prior to TAG on October 20th. We need to get all of the command products loaded for this event. One of the big items is our natural feature tracking catalog that needs to make its way to the spacecraft. We also have a series of burns planned with our navigation team to get the spacecraft phased just right for our TAG on October 20th. So we'll be doing testing. We'll be finishing up the review and test of our final command products and getting them sent up to the spacecraft over the next 3 weeks.
Thank you. Our next question comes from Marcia Dunn with Associated. Our next question comes from Marcia Dunn with Associated Press. Your line is open.
Yes, thank you. I'm wondering, why would you have to wait until January for a second try to scoop up some material? And is it only 2 tries? And why can't you just go back in the next day and repeat for Nightingale? Just sort of help me understand why it's so laborious. Thank you.
That's probably for Mike.
This is Mike Moreau from NASA Goddard. I'll take that. So the first question was, why does it take us a couple of months to reset? Well, we're going to spend the first few weeks after TAG just assessing how much sample we collected and also determining if the spacecraft has been damaged in any way or any of the instruments have been compromised as part of the TAG attempt. Once we're done with that assessment, if we need to go back again, we have to get the spacecraft back into orbit and then conduct these series of phasing burns and trim burns to line up the position in orbit to depart for the next TAG attempt, and that takes another 2 or 3 weeks. So just giving the team enough time to get through those activities and also just giving them a little bit of a breather between these very intense events is why it takes that long, why we put that out in the future. And then there was another part to the question, which was just why don't we go back to Nightingale? One of the things we'll do as soon as we're done with the first TAG attempt is we'll look at the imagery we collected when we're backing away and see how much the site was disturbed. But at this point, we have to assume that if we've touched the surface and disturbed the surface, we won't be able to just go back to the same place again. So we'll be taking time to assess that in case we need to go and try again at Nightingale later. We actually have 3 nitrogen gas bottles on the spacecraft, so we can make 3 contacts with the surface. And if we wave off before contacting the surface, we can do that over and over again.
Okay, thanks. We're ready for the next question.
The next question comes from Nell Greenfield Boyce with NPR. Your line is open.
Hey, thanks for doing this. I appreciate it. Could you talk about, you said you might know the quantity of material, assuming everything goes well with the attempt and you gain material. Did you say it would be late October, you think you would, have the results of those different measures you indicated to see if there was material? And also, could you basically compare, I know this is the first time NASA has tried to do this kind of sample return, but there have been other attempts. Could you give a comparison to how the material in those compares with what will be got here?
Sure.
That's very inelegant. I apologize, but I think you get the drift.
Yep. This is Dante. I'll take that. So we do have a planned, what we call operational key decision point on October 30th, and that's where the team compiles all of the information from the different analyses that I described. And we're keeping Thomas and Lori fully informed on a daily basis. We'll be providing them a summary of all the work that the team is doing, and we'll know where we're trending on the likelihood of collecting at least that 60 grams of sample. But that October 30th date is the official decision point where I work with Mike and project management team, and we put forward our recommendation to the agency, and we say either we think we are good and we should go for STOW, or we think we're not, and we should start planning a second tag event. And so Thomas ultimately will come in with his decision, and together we'll go forward with whatever plan is agreed on at that meeting. In terms of comparing to other sample return missions, we work closely with our colleagues at the Japanese Aerospace Exploration Agency, and they have successfully contacted the surface of asteroid Ryugu with their Hayabusa 2 spacecraft and are on their way home, and that sample will be back in a few months towards the end of this year. There are some key differences. We're great partners with them, and we work well, and we're actually excited to see their samples and bring them back. They're using a technique that's kind of a ballistic collection. So they fire essentially a bullet that struck the surface of the asteroid, and then they have a sampler horn where the fragments from that impact get pushed up into the horn and right into their sample collection chamber. So they're limited in the amount of mass that they can collect through that technique. They're talking about milligrams or tens of milligrams, where we're in the order of grams or tens or maybe hundreds of grams of sample that we're bringing back. So that's one of the key differences. They did touch down in 2 different locations on asteroid Ryugu, including near a artificial crater that they made with their small carry-on impactor experiment. So they will have some comparative science. They kept those samples separate from each other, and we'll be able to see what 2 different areas of asteroid Ryugu look like. But really combined, it's an amazing data set to be able to have information from these 2 near-Earth asteroids, which superficially look similar to each other, but in detail are actually quite distinct. We think the mineralogy is very different across the 2 asteroids, and we're really excited to have an international coordinated sample analysis program looking at both of the materials from these asteroids and learning a lot more about asteroids in general and these carbon-rich asteroids in particular.
Okay, thanks. Next question.
The next question comes from Bill Harwood with CBS News. Your line is open.
Thank you very much. One real quick question on your minimum collectibles. How solid is that 60 grams? And what I mean by that is if you do your moment of inertia spin up and you find you've got 45 to 50 grams, would that automatically mean you'd make a second attempt, or would you guys talk about that and perhaps settle for less? I'm just wondering, is there some hard and fast line that you're committed to meeting? Thanks.
Do you mind if I take that, Dante, and you correct me if I'm getting it wrong? It's Thomas, right? Just the way the organization works here, and because of the fact that this is such an important decision, it's a discussion with multiple people. The good news, I actually feel like, and Dante and I talked about this multiple times, as well as Lori and her team too, we're all aligned. So suppose we were in a case where it's just a little bit under the 60, frankly, we will also know how the spacecraft is doing, the performance overall. The discussion that we're going to have is very much focused on, what's the right thing to actually maximize mission success. And for us, I think the requirements are really good for us to organize the mission around. It's absolutely clear that when you go and do these things, kind of error bars matter. And judgment matters too. And I just want to tell you kind of what I've learned in this job, as well as in decisions very similar to this, is, the most important thing is to listen really carefully to the people who actually strongly depend on this sample, which of course is the principal investigator and his team, but also the people we heard from here that are flying the spacecraft and also have a level of confidence of what's there. So I don't think of it as a hard and fast, so we really want to use judgment when it's kind of in the gray zone, so to say, because at the end, I want to make sure that we make the decision to maximize the science. Dante, what would you ask? What would you add? I'm sorry.
I think that's absolutely right. And we actually have rehearsed this decision-making criteria. We've talked about it extensively with Thomas and Lori and their teams at headquarters. We have this gray zone, as Thomas alluded to, where it's not obvious what the path is. And that comes down to, what do we think is the right thing to do? What does the spacecraft team think the right thing is to do? And what is the level of confidence we have in that number? So we're ready for that conversation. We're all on this together. It's a great team. We have a great relationship with our colleagues at headquarters, at Lockheed Martin, at Goddard. And we know that we can make decisions based on the best information we have available to us.
Okay, ready for the next question?
The next question comes from Don Halduck. Your line is open.
Hi, this is Don Haladiak from the CBC. My question, and thank you for doing this, my question has to do with OLA and the loss of the low-energy laser. Is there enough backup or redundancy for the altitude determination to make this tag successful?
I can start with this one. So OLA did an amazing job for us, and in fact, it has met all of its mission requirements in terms of mapping the asteroid at an unprecedented scale of a 5-centimeter spatial resolution and less than 2-centimeter vertical precision. So OLA is not and never was planned to be used for the tag event. We did have a LiDAR-based system. It's still on board. It's called the Guidance, Navigation, and Control LiDAR system. That was the original design for tag and corridor monitoring as we approach the surface. But that was really where the 25-meter original requirement was being met. The LiDAR was not capable of the high precision contact that we need to have. So the natural feature tracking system that Mike described is the only system that's estimating the state and position of the spacecraft relative to the asteroid surface. So we were sad to lose the low-energy laser transmitter on OLA, but it did its job. It did an amazing job, and it's not required for the tag event in any way.
Thank you.
So Dante, this is Mike Moreau. If I could just add to your response. I referred earlier to the amazing work that some of the navigation team members and other Lockheed Martin team members have done to get to this precision navigation capability. And the amazing OLA data set was one of the key inputs to that. Without that data set, it would have been very challenging to get to the level of performance that we have with the system today because it provided this independent measurement that we were able to use. So.
Okay, thanks. Next question.
The next question comes from Michael Greshko with National Geographic. Your line is open.
Thanks so much. A couple quick questions related to the sample. So Hayabusa 2 has taken 2 samples and has stored those separately. If you do touch down at Nightingale and then Osprey, what kinds of procedures are in place for discriminating the samples from those 2 different sites? Also, earlier this week, the OSIRIS-REx team published results that Bennu had fragments of other asteroids, namely Vesta, on its surface. Based on those results, do you have any rough estimates of how much material from other asteroids you might pick up with this?
Sure, I can take that. This is Dante. So one of the key factors in a decision for going back for a second tag attempt is the concern that you just alluded to. That is, we will mix together anything we collected at Nightingale with anything that was collected at Osprey. So disentangling the samples will be the work of the curation team and the sample science team on the ground starting 3 years from now in 2023. So to me, that is one of the factors that would lean against going for a second tag. If we had verifiable macroscopic material that was just under the 60-gram requirement, I would be concerned that maybe we do compromise some of the science by bringing in Osprey-located material and mixing those 2 together. So that's part of the trade space that we'll be thinking through the cost, the benefits, and the cons to going to an Osprey tag attempt. And then in terms of the Vesta material, that's a really exciting result. There's a very small amount of the pyroxenes that are characteristic of asteroid Vesta on the surface. We are certainly going to look for those. They're a key part of our sample analysis plan to go find that. And we don't really see evidence of other kinds of asteroids right now. We're trying to understand if there might be other types of asteroids that are apparent in the data collection. But it's not obvious that we see anything except that Vesta material. That was a surprise, one of many scientifically that Bennu provided, and a very exciting one because it allowed us to understand more about the dynamical history of this asteroid and its origins in the main asteroid belt originally. So I'm hoping that we get it, but it's like I would say less than 1% chance that we're actually going to collect the Vesta material, unless it happens to be abundant at the micro scale at a different level than we see expressed in the large boulders where it's apparent to us from the remote sensing data.
Thank you.
Okay, next question.
The next question comes from Craig Smith with KGUN-TV. Your line is open.
Hi, for Dante Loretta, I'd like to just sort of zoom past all these challenging maneuvers and assume that you've already reached that moment where you're looking at that sample chamber back here on Earth. What's that moment going to be like for you, both scientifically and just personally?
Yeah, it's hard to predict what the future is going to be, Craig, but I can compare it to maybe the launch day, which was probably one of the proudest, most exciting times of my career. Which it's transcendental when you reach a point in a project like this that you've dedicated almost your whole career to see a success like that come together and the team recognized for their efforts and celebrating together. It's going to probably be Christmas in September, the best Christmas present I've ever had. These pristine samples from asteroid Bennu that I've been literally dreaming about for, at that point, almost 20 years of my life. So we have an amazing sample science team that's gathering on Earth. We're working through our sample analysis plan in great detail, identifying laboratories. It's going to be a lot of fun because we're going to work with the best analytical facilities on Earth. And just to learn more about all of the different analytical techniques has been a real great science boost for me. And it's going to be a kind of a world tour of Bennu samples to understand everything we can learn about this asteroid, bringing together the best and brightest minds from all over the planet.
Thanks, Dante. We have time for just one more question. And operator, could you open that mic?
Thank you. Our final question comes from Kimberly Cartier with American Geophysical Union. Your line is open.
Hi, thanks so much for taking this last question. At the very beginning of the presentation, Lori talked about the Apollo 17 samples that were opened after so many years. And I know everyone's going to want to get their hands on the OSIRIS-REx samples as soon as they touch down. So I was wondering if there is any discussion about having a similar legacy program for some of these samples for scientists in the future.
So I don't know if Dante wants to take that, or I can. This is Lori Glaze.
I think Lori,
and so there,
for you.
Okay. So we have planned to save a significant fraction of the returned sample for future generations. This is actually a standard within our NASA sample return programs that the samples, when they come back, we are going to save a substantial portion of that will be preserved. And so the team will be working with a fraction of what actually gets returned and doing their scientific analyses on those. So you're absolutely right. I think the Apollo program has really shown us just how important it is to save and preserve those samples in a pristine state that allows us to address questions that we didn't even know we would have at the time those samples were collected. So we very definitely will be doing that in this case as well.
Okay, thanks everybody. I appreciate the participation. If we did not get to you, please do send in your question to us. My name again is Gray Hautaloma. My contact information is at the media resources page at nasa.gov, as well as Nancy Jones at Goddard and Aaron Morton at the University of Arizona. And our contacts are on the advisory that went out announcing this event, which is also at nasa.gov. There's a playback number for this event. It'll be available in a couple hours, up for about 1 month. If you want to dial 866-430-8793, you can hear that there. And audio will also be posted by Goddard, along with today's graphics, at the visualization site, which is linked to in the feature, which is up right now on the front page of nasa.gov. So again, I want to thank everybody for participating, and please join us again in a little less than a month for the TAG event. We're going to have some briefings about asteroid science and other aspects of the mission on the 19th, and then, of course, looking forward to TAG itself on the 20th, which will have a live broadcast associated with it. Thank you, everybody, and this concludes our event.
That concludes today's conference. Thank you for your participation. You may disconnect at this time.